Okay, so thank you so much for making it to the end. It's been long. I'm happy we have a full house right here. That's a joke. So what is this talk even about? Well, first of all, distributed models over distributed data sounds really complex, but actually we're going to be talking about something much more simple, which is, hey, I'm a data scientist. Databricks, other people are saying, oh, more data equals better. So should I use Spark ML for all my stuff? What about my single node models? I really like those. Can I use my single node data science approach in the big data land? When does this even make sense? So what we're going to do is we're going to start by tracing the idea. Does more data always equal better models? Does that mean that we should always be using distributed models? When is that not true? And then I'm going to be showing you an alternative approach to actually using traditional single node Python machine learning and actually applying that in parallel by things like Spark user-defined functions. Okay, so to get started, let's talk about more data equals better models. This was actually a slide from our CEO saying, obviously you want to throw more data at the problem. More data is better. That means you should be distributed on Spark. Once you're distributed, single node machine learning doesn't work, so then you have to use Spark ML, yada, yada, yada. So clearly Spark is the answer for everything. But if you're a data scientist and you've tried to use Spark ML, you've probably noticed, man, I actually really like my single node machine learning libraries a lot more in some cases. There's a lot of functionality in Spark that doesn't really work that I miss. And so data scientists are always coming to me and saying, do we really need to switch all our code to Spark? And do we really need to use all of the data? The answer is totally not. But let's dive into it. So where did this idea, more data equals better models, even come from? Well, back in 2009, Peter Norvig came out with this paper. And in it, he says, definitely with simple models and a lot of data, you can do better than more elaborate models. Okay, so that's point one for the more data equals better model camp. Furthermore, back in 2001, Benko and Brill showed that when you increase the amount of data, you got a clear increase across all of your models. So better data, better models. And then finally, there's this nice blog post I found from a while back where the Stanford professor is talking about his class on the Netflix challenge. And he's basically saying, look, the teams that used a lot more data clearly beat the better designed algorithms using less data. So this should be a case closed. More data equals better models, right? Well, not so fast. So first of all, let's go back to that Norvig paper. Norvig, which everyone cites as saying more data and simple models beats more complex models, was actually talking about NLP, and specifically, he was comparing the traditional approach of NLP, such as encoding hard-coded language rules, versus statistical learning. So his point wasn't that simple machine learning models with more data beat more complex machine learning models with less data. His point was that machine learning models actually outperform experts' hard-coding language rules. People always miss that part. Second of all, actually, one other point about Norvig is that in a 2010 talk I found, people were asking him about this, and he was actually saying, we've started exhausting how far we can get with simple models. We need to start looking into more complex stuff, aka deep learning. And I think everyone knows Google does a little bit of deep learning. So on the Netflix data set, so the actual winning team said, in fact, getting more data after a certain point didn't really help because that data wasn't adding a lot of new information. Better models actually got us there. And furthermore, this is actually from one of the Netflix engineers showing how more data actually improved the model. So you can see at the beginning, there's a nice rise, and then boom, flat line. Okay. And one thing else to remember, so going back to that corpus that Norvig was using, and the one that Benko and Brill was using, and even the one that Netflix was using, we're talking less than 5 gigabytes of data total. That was big data back in 2010, right? So all of that fits inside a single node. So where does that put us in terms of more data equals better models? Well, there's a few patterns that we need to call out. Pattern one, we need to think about bias versus variance. So how simple is our model and how simple is the domain that we're trying to fit? Ideally, we want our model to be at the same level of complexity as the domain it's trying to model. If it's too simple, it's not going to be able to capture everything within that domain. But if the model is too complex for the simplicity of the domain, it will overfit on details that don't actually matter, and that will stop things from generalizing. So once we start thinking in that frame, we start noticing a few patterns. So within different domains, certain domains, such as highly structured data, we're talking our classic CSVs that you might find on Kaggle. These are considered high bias domains. They're very simple. And it turns out that when you add a lot of data after a certain point, you've kind of exhausted the complexity of the domain. So when using non-deep neural nets, more data doesn't really add much value. And in fact, that sweet spot where you get enough data, more often than not, falls very firmly within a single node framework. On the flip side, if you use very large, very deep neural networks on high variance domains, such as text and image and video and time series, actually more and more and more data, the models will continue to improve. And it was actually the advent of mobile data and internet scale data, specifically with the semi-structured and unstructured data sources, that led to the birth of the modern deep learning back in the early 2000s, right? But this does not apply across all data domains. Just because you pulled some data out of a database doesn't mean more data will improve your model. So to conclude here, what have we learned? We've learned that in high variance domains, semi-structured or unstructured domains such as text, image, video, time series, more data will improve your models if these are high variance models such as deep learning. But in high bias domains such as your standard relational databases, you're only going to get improvement up to a certain point, and that's definitely going to be within the single node data science model. Okay, so let's dive into the deep learning section. Now that we know that more data is better with deep learning, should we always try and do these big distributed clusters? Not necessarily, actually. And the reason for this is that transfer learning, using pre-trained neural nets and then doing a small update on your specific domain, more often than not actually beats out training your model from scratch. So one specific example was Matej Zaharia, one of the co-founders of Databricks, ran a deep learning benchmark at Stanford where people competed to see who could achieve a certain level of performance on various tests and who could do it the fastest and the cheapest. And in many categories, the Fast AI team won using very small architectures relative to other teams for a fraction of the cost. And a big part of why they were able to do that was via transfer learning. The same Fast AI, one of the members of the Fast AI team actually published a paper on NLP showing that when he compared transfer learning on just a few hundred samples, he was able to outperform a net trained from scratch on 100x the amount of samples. So in this case, a few hundred samples was all he needed to get much better performance. If he had tried to load all of these other data points and train from scratch, not as good. So what can we take away from that? The idea is, even if you're in a deep learning domain, if that has well-established pre-trained networks, let's say it's on image or video or text, you're better off using transfer learning on a small set of examples using those pre-trained nets rather than trying to train your network from scratch against all of your data. Now, if there aren't any pre-trained networks that are broadly available, well, then you're out of luck, and you may need to go into training everything from scratch, and then maybe we can talk distributed. So I work at Databricks. Databricks' whole story is about distributed data. You may be like, wait, what is this guy doing? That's kind of like breaks the whole story, right? Where is the magic? But actually, the reason I'm telling you about this is because I think there's actually something even more powerful than the traditional Spark ML that's going on right now, and most people don't know about it. I think this is one of the most exciting parts of ML productionization happening today. I use it a lot internally, running some of the internal analytics at Databricks, and I'm excited to talk to you guys about it. So the first step to this argument is something called the no free lunch theorem. So basically this says that given any two models in machine learning, when we look at all different possible problem space, these models are going to be roughly equal in performance. Or practically it means that without knowing much about a problem, we don't know what model will be right for that problem. And if you're a data scientist, you've run into this. You might have a few ideas like, OK, everyone always uses XGBoost on Kaggle. But you still need to try out a lot of things. You need to do some hyperparameter optimization. You might want to try a range of different models. But the big pattern here is no one knows which model to use up front. So you got to try out a lot. And furthermore, trying out a lot of models in general tends to be embarrassingly parallel. We can distribute this. We can do many models simultaneously because more often than not, these models don't have dependencies with each other. And that's really, really great for cluster computing because it means that instead of doing a for loop and doing first model, second model, third model, you just think about all the possible models you want to do, and you just do them all simultaneously, right? That's kind of a different way of thinking about stuff. So what I'm showing you here is called the Pandas user-defined function, Pandas UDF. What this code is basically showing, it's just some normal Python code. It's a OLS model, entirely Python. There's no Spark in there. But by doing this little pandas decorator, we're now able to use it in a Spark function. So let's see if this works. So this bit right here, that data frame, that's actually a Spark data frame. And this apply right here, this is taking that normal single node Python function and distributing it horizontally across all these different partitions in Spark. So this turns out to be an incredibly powerful idea. How we've used this internally. We worked on a forecasting problem where we have many, many different customers. Each customer has some time series associated with that customer from telemetry data. The time series itself is maybe recorded at the daily level. And so if we have a year or 2 years worth of data for each customer, we're talking about less than 1,000 points per customer. That's not very much. So in terms of models, if someone told you Spark ML for that problem, you should, go in the other direction. But when we talk about tens of thousands of customers, how do you come up with a clean way to develop a specific time series over each customer? Our data science team had tried to use Spark gapply, and they ran into this problem where after 4 hours, basically their cluster would crash from memory overhead. We took a single node forecasting model, essentially, just wrapped it in this Pandas UDF, and then grouped by customer ID. The whole thing ran in 15 minutes. Now, if you want to get extra points, you can put some MLflow in there so that MLflow is recording all of the different results from each model run on each of the worker nodes. And then you just drop into your MLflow UI, and you can say, OK, these are the best models. These ones aren't doing great. That is a really powerful pattern. The other bits that I think data scientists don't think enough about is all the stuff they have to do around the modeling. How do you actually set up a reproducible environment? How much time do you spend actually installing stuff on new clusters? So I love this plot to actually think, OK, is this actually worth me trying to automate? Here's how much time you get back when you try and automate things. Now, the piece that we always miss as technical developers is, in theory, we save time, but in practice, it's actually yak shaving. But let's just pretend in theory we're doing great. So rather than actually installing everything from scratch, you want to find out, how do I take all those things that we have to do every single project and automate them? I think the machine learning runtime is one example that does this great. People were spending so much time trying to get deep learning stuff to work with GPUs, and it was a huge pain. With the ML runtime, boom, it's already baked with the GPUs. This also became really important for us when we wanted to actually productionize our forecasting solution, because having every single node in the cluster already pre-populated with the machine learning libraries we needed to productionize saved a ton of time and complexity when we were actually deploying. So these little things really do add up in terms of the iteration speed. Furthermore, we've talked a little bit about MLflow, but where does MLflow actually sit into this? Data scientists, again, they think a lot about models, but really the most important productivity metric is how fast can they complete a full iteration cycle, from setting up their environment, training a bunch of models, finding the best one, pushing that off to prod, and then monitoring the prod. And then when a model starts decaying or they need to add a new use case, they can go through that cycle again. Trying to pre-roll your environment using some idiosyncratic structure or trying to inherit something from engineering, people often find that the level of abstraction that they're working with isn't actually appropriate for their projects. Using something open source, whether it's MLflow or not, allows your team to scale much better. So here's a final bit. So data scientists spend a lot of time actually thinking about building models, but then when it comes time to push them to the rest of the organization, that's where they struggle. And we hear a lot about the science experiments in data science. A lot of people focus on REST API. That's great if you're working with engineers, but many enterprise actually run on SQL, not REST APIs. So how does this play with your models? Well, that MLflow model, it turns out you can actually just register it as a Spark SQL model. And now, once that is a Spark SQL, your business analyst can use your deep learning just as a SQL function. And because this is in Spark, it also works with R, Python, and Scala. It works in both structured streaming and batch. So thinking about serving models via SQL to business analysts is a very different thing than I think a lot of people are talking about right now. This was very powerful for us. How we use this internally is once we completed that forecasting initial model, we pushed it out via SQL, and we actually put MLflow inside the function so that whoever called that SQL function, we automatically logged which accounts it was running against, what the results were, and then that allowed us to go back to management and say, hey, look, this model, it's been used by all these people, and it's produced this much impact, and then that led to more investment. So actually figuring out a way to track your models and attribute impact is critical. So what did we learn from all of this? Point number one is that generally distributed data and distributed and big ML, Spark ML, whatever, only works in situations where you have no pre-baked deep learning or you have a ton of high variance data. But in general, more often than not, actually sampling down the data and using a single node model is completely appropriate. That said, data scientists always need to do multiple models, and instead of doing one model after another, it's better to think about how to do all of your models at once and then use a Pandas UDF to scale this out across partitions of your data. So that's where the distributed model on the distributed data comes in. But when you use this newfound skill, you might find yourself generating in one go tens of thousands of models, at which point you need a way to track those models. That's where the MLflow distributed on the worker nodes comes in. That gives you a very clean way to track all your results, pick out the best one, and serve it. The next step is how do we serve it in an easy way? Well, you can do the REST API thing, and that's one thing. But more often than not, enterprise runs on SQL, serve it via SQL function. That's great. And once again, putting MLflow to track who's actually calling that serving closes the loop and brings us back. So that's my talk. I will open it up a little bit for questions. Thank you very much. Question in the back.
Yeah, thank you for the talk. I actually have a complaint and a question.
Okay, lovely.
Considering the complaint, so all those Pandas UDF stuff is actually cool until you are not the vector type or vector UDF type is not actually a first citizen in the in Spark. because most of the models are actually most of the libraries are actually supposed to get NumPy arrays in it, or when you're working with Spark ML pipeline, a vector type. And in that case, you can't just stick a vector type into Pandas UDF. It would not just work. So please, there's a Jira ticket there. If you have an opportunity to implement vector type as a first-class citizen for the Spark SQL types, that would be really, really great. And the second thing is that there's really lack of documentation and examples of using custom transformers and custom estimators, because Spark ML has a really cool grid search CV, which can tune your hyperparameters in parallel. But still, every example, just have an example of Pandas UDF, but you can have your custom transformer, custom estimator just stick in the Spark in my pipeline. So basically, why did not you present this kind of stuff? Is there a problem with that?
Yep, these are both fantastic points. So point number one, Pandas UDF doesn't take in vector types. And point number two, there's some native stuff in Spark that does a lot of hyperparameter optimization. Why aren't you talking about that? That sort of thing. Fantastic points all around. So before I was at Databricks, I was a data scientist who actually became a Databricks customer. And working with my other data scientists, trying to get them to use Spark, I discovered three concepts. And if you were in my tutorial earlier, you've already heard these. But I found I couldn't get data scientists to switch their workflow or switch Spark unless I hit all three of these things. Point number one, show 10x the value. How does your solution improve by an order of magnitude across what they're already doing? Many times people have solutions, but they're marginal improvements that don't justify the switching cost from your workflow. Point number two, show that improvement in 60 seconds or less. And then point number three, show it in 3 steps or less. If I can show all three of these things, I could get data scientists to switch. Data scientists are the most stubborn people in the world. You ask them about RStudio versus Jupyter, and they're like, no, I'm never going to leave RStudio. Okay, so going back to your question, why didn't I talk about the vector stuff or the MLflow? The problem that I see with a lot of data science teams in particular is they've been working in Python. They've been working in Pandas, scikit-learn, XGBoost, whatever. And if you come to them and you say, hey man, I need you to rewrite everything in Spark, well, that is a huge switching cost. And that's a problem. So there's a lot of Python teams that are like, oh man, we're running into scaling issues. How do we scale this? But also they're so deathly afraid of having to do this big thing where they load everything into Spark. So the reason I showed it like this is because you want to meet people in their current environment. And you want to show immediate value that gives you a 10x improvement over what you're currently doing. So if we think about what does that 10x improvement actually look like, I have here just a normal, pretty lame Python function that's calculating the averages. And I put some MLflow code just to make it more fun. Now, perhaps let's assume this is a really dumb model, okay? It's not a very interesting one. But it's just all Python. I'm taking in some pandas. But now I want to actually use it in Spark. What do I have to do that? I import Pandas UDF, and basically that's it. Now, I'm covering up some magic here, which I'll tell you in a second. But let's think about it. Now that single node Python person is able to run their stuff on a distributed cluster that can scale out horizontally. So, with some caveats, if the data gets larger by orders of magnitude, now their function can handle it. Furthermore, we did that in 3 steps. I mean, it's probably 4, but who's counting? And finally, if you actually run this, I mean, it's not going to take like a ton of work to rewrite, right? So going back to the idea that you meet the data scientists in their environment, you give them a very quick fix that actually gives an order of magnitude improvement. If your team is already using Spark and they're using vectors and they want to use the Spark ML, I don't say do this. I say use the Spark ML. Do whatever you're currently doing that's going to deliver value. Actually, in this example, so let's just walk through how it actually worked. I took my Python function. I did a little bit of a trick here because I was lazy, which is when doing Pandas UDF, what's actually going on below the covers, there's you have your Parquet data. It transfers into another file format called Apache Arrow, which was done by the Pandas and the dplyr guys. And then that's where the Pandas runs, and then it translates back into Parquet. But that bit where you need to go from Arrow to Parquet, you need to provide Spark as schema. So that's why I'm taking some data frame and then just grabbing a schema here. That's what I have to stick in. I'm also setting an experiment ID so the logging shows up over here, which I haven't run yet in this notebook. But other than that, it works. So how would you actually call this thing? Well, once we have our distributed data frame, I would group by my partition ID or my user ID or my product SKU ID, and then I apply my single node Python function. That's what it looks like. And again, when we actually run this, this then records everything. So the other bit where I talked about actually the SQL, I'll just show that really quick. I was working with some data scientists, and they're like, okay, yeah, Thunder, this stuff's really cool, but like, can you take some of our code and then show us how many steps it actually takes to put the MLflow and the SQL deployment in there? And again, I really like doing things quick and simple. So what we did is we grabbed some scikit-learn example. This is just from one of the examples on their website. I started by putting mlflow.startRun to specify I'm doing some runs. I logged some models. So that's what that looks like. And then so again, not super interesting, but you can see I've logged 2 decision tree models. Then once I have those models, I create an example data frame in Spark to actually run the models against. And whenever you run a model in MLflow, it generates a hash that corresponds to that experiment run. So hopefully our internet stabilizes here. So if I drop into my model run, we'll see at the top of the screen, there's this hash that's specific to that model. And then here are the 2 models that we actually recorded. Again, if we actually look at the code, that was done in about 3 steps. Because first I imported MLflow right here. I say with mlflow.startRun to start my experiment. And then I do mlflow.log parameters and log models. Once I found a pretty good model, I'll grab that hash. You can also have a function that just grabs the best performing model or anything like that and actually registers that to a Spark user-defined function. Now someone can use that single node Python function with Spark. And again, this works on R, Python, whatever. To take it a step further, I'm just going to do this additional step where you do spark.udf.register. And now I can use it as a SQL function. The 0 here is just because I was lazy and I made a random string. It doesn't have a column name. If we actually had column names, you'd stick those in instead. But again, this bit now works on Delta, works on structured streaming. The one caveat, though, is it's still not going to be super duper fast because the underlying Python is a black box. And furthermore, the partition that you're running your Python over has to be small enough to fit on a single node. If it's too big to fit on a single node, then the Python function will get an out-of-memory error. But again, this was pretty quick. And now we actually have something we can give to our analysts to run. We have a distributed way of training models, and then we can use MLflow to actually track and serve all of those models. I think, how are we doing on time? 10 minutes? I think we have time for a few more questions. Yes?
I have 2 simple questions for you. You mentioned about Panda UDF.
Yep.
The first one is that you say you have many customers that you want to do the time series model for each of them. So my question is that you mentioned about using Panda UDF for doing the time series model for each of them. So my question is that whether you could use this Panda UDF with the deep learning model like TensorFlow or Keras as well. And the second question is that this Panda UDF and Keras, they seem pretty close to me, like both of them might be distributed data frame. So could you elaborate more about their differences?
Yeah.
Thank you.
So the 2 questions, can you use this with deep learning models, and what's the difference between the Pandas UDF and the koalas? So for the first one, you absolutely can use it for deep learning. We've talked about the situation where you're applying your model across partitions of your data, subsets, But also, there's a number of different cases where you can use this for hyperparameter optimization. So if you set up a different partition of your data where each data has different hyperparameters, again, you can use this to distribute that out. That works for deep learning as well. The one requirement, though, is that the input and the outputs need to ultimately be pandas data frames. So if you do some transformation inside your function to make sure that those map directly into Keras in some way, and then they output a pandas data frame, then you're OK. Question number 2 is, what's the difference between this and koalas? So the motivation behind koalas is to create an interface for Spark that feels a bit more Pythonic. Because if you're a Python developer and you use Pyspark, you're probably going to you probably have noticed there's a lot of bits that don't feel very natural. So pandas is to try and map on top of that. There's a single node version of pandas and a distributed, but the pass off is a little, it's not totally robust at this point. This is purely about how do we take a single node function from pandas and then distribute it over many partitions of data. So was that clear, or do you want me to go a little bit more in depth? OK. OK, another question. Yes?
Hi, I was speaking to some Databricks guys, and they showed me HyperOpt.
Mm-hmm.
They showed me HyperOpt with Spark trials. I was wondering, how does that compare to this kind of workflow?
Yeah, totally. So the question was, what's the difference between HyperOpt, which is Spark native, compared to using something like Pandas? So again, I think it's really about meeting your team in wherever their workflow is currently. HyperOpt being very Sparky means that if your team has already built all their pipelines out on Spark, then that might be a very natural fit to start using that for their hyperparameter optimization. On the flip side, if your team's coming from native Python development, then this might feel a lot more natural. Furthermore, I think HyperOpt is more baked as a product in terms of, here's this package, it does something really well. It was designed for hyperparameter optimization, so it has a single purpose, whereas Pandas UDF is a bit more low level. Yes?
I was thinking of doing something similar using Dask.
Mm-hmm.
What is your opinion, pros and cons comparing to
Good question. So the question was, how does this compare to Dask? We were having a big company thread about Dask, trying to figure out where we stood on it. And then we found out that some users were actually installing Dask on Databricks, and it worked fine. We're like, oh, that was lucky. But in terms of using Dask, I personally don't have a set opinion on it yet. I know Dask is really a Python-first community, and you're going to get a lot of benefits from that. Whereas even though Databricks and the Apache Spark community have been investing a ton in Pyspark, it's still largely from the perspective of like Scala developers, although we have a ton of Python people internally. So you're going to get a very different experience and flavor. On the flip side, though, I think when you enlarge your scope to look at production pipelines, rather than just the Python data science bit, and you start looking into the questions about what about productionizing large-scale data on large clusters, then I think the Dask question becomes a little bit harder. For instance, with MLflow and Delta, I think the real killer use case that's coming up with MLflow and Delta is MLflow has these hashes that it associates each run to. And that, in turn, associates different models and different code to runs. But the piece that's missing there is connecting the data and the state that you ran the model at to that run, right? But if you actually look at something like Delta, Delta has these atomic changes on the data. And whenever you do that atomic change, there's a hash associated with that. So when you combine these two, suddenly you have a way to reproduce at-scale machine learning models on data in the state that the data was when the original experiment was run. That sort of stuff, when actually thinking about scale, is extremely exciting and powerful. And I haven't heard that sort of scaling happening on the Dask side. But maybe that's just because I'm ignorant of something that they're working on. So that would be my opinion on that. OK, final question. Yes?
Thanks. So yeah, you showed an example where you basically define a UDF and you use it in another language like SQL. So assume you have a pipeline in Scala. How would you register the UDF without using a notebook?
Okay. So, good question. So to be fair, I don't have a fully baked answer on this because internally we're using Python for most of our machine learning stuff. It gets a little funky on the Scala side around jars. So let me take a think and then we can talk offline about that one. But I don't want to come up with something half-baked. Okay, final question because I kind of whiffled on that last one. Or not. Okay, well, thank you so much for coming to my talk. I hope you enjoyed it.